In this video, we're going to talk about the stability of atomic nuclei and radioactive decay. Now, we know from last time that atomic nuclei have, a very small size, and that the average radius of an atomic nucleus is given by this equation, where A is the number of nucleons, that's protons plus neutrons, and this R naught is 1.2 times 10 to the minus 15 meters, right? And this R naught is roughly the radius of a single hydrogen nucleus, right? Basically the radius of a proton, or at least how close an alpha particle can get to a proton without being turned around. And what this suggests, right, is that we know that the volume, if we assume that the nucleus is roughly spherical, right, so that we have these particles and they're packed in very closely together so that the nucleus is roughly spherical, and these particles are both protons and neutrons. So let's say proton, neutron, proton, like so. Then if we assume the nucleus is roughly spherical, we know the volume of a sphere is 4/3 pi r cubed, which means that the volume of the atomic nucleus is approximately proportional to the number of nucleons, right? It goes as r cubed, and the radius goes as nucleons to the 1/3. This also suggests that all nuclei have about the same density, right? So every single atomic nucleus has roughly the same density as every other one. But there is a problem with this. And the problem is the electric force, right? We know from earlier in the semester that the electric force is K Q1 Q2 over R squared. And our K is our Coulomb constant, which is very big. And our R for a nucleus is on the order of 10 to the minus 15 meters. Which means this Coulomb force in the nucleus is going to be really, really huge because we have protons that are packed in really close together. And if this was the only force acting, the nucleus would blow apart, right? There should not be an atomic nucleus. But it turns out that nuclei are stable because of a different force, as a short-range force called the nuclear force. So the nuclear force, right, is short range, and by short range, I mean acting on sizes, distances roughly equal to an atomic nucleus. And it is an attractive force that acts between both the protons and the neutrons. And it is stronger than the Coulomb force. Right, so it's stronger than our Coulomb force. It's very short range and involves both protons and neutrons. Whereas our Coulomb force, right, only involves charged particles, so it's only between the protons. But this, right, the other issue, there is another issue, is that as a nucleus gets bigger and bigger and bigger and heavier and heavier and heavier, this distance, this R, becomes a little bit too big for this nuclear force to really hold your nucleus together. Right? We want, right, for this, because this is a very short range force, we need the size of our nucleus to be really, really small. And if I pack more particles in there, because all nuclei have roughly the same density, if I pack more particles in there, the radius is going to get bigger. So for light atoms, for light nuclei, they're most stable if the number of particles is equal to Z, Z being the atomic number. This is why for most nuclei, right, they pretty much have either fewer neutrons than protons or the same number of neutrons as protons. But for heavy nuclei, right, where you have a lot of particles, right, where the atomic number is big, most heavy nuclei are most stable when the number of particles, the number of nucleons, is bigger than the atomic number. Because as the number of protons gets bigger, right, then you have more pairs that can exert Coulomb forces on each other. And so you need more neutrons, because remember, this nuclear force involves both protons and neutrons. You need more neutrons to help keep everybody together. And there are no stable nuclei above atomic number of 83. So if we plot, right, the neutron number, how many neutrons against the proton number, right, for most small nuclei down here, they're roughly the same amount as protons and neutrons, depending on the isotope. But the most common isotopes of most atoms, for smaller atoms, smaller nuclei, have the same number of protons as neutrons. But for bigger atoms, right, you can see this is the N equals Z line, where number of protons equals the number of neutrons. For heavier nuclei, you need more neutrons to balance out, so that this nuclear force can balance out this Coulomb force. But when we get up to about here, right, there are not enough. There just aren't enough. So there aren't any stable nuclei. What happens, the nuclei don't just explode apart. What they do is they just decay. They'll lose a particle here and there, and they decay into something else. Now, it turns out that for atomic nuclei, the total energy of the system is less than the combined energy of the separated nucleons, right? So if you add up, right, the total mc squared for the whole thing, right, total mass c squared, that's going to be less than the individual combined energy for all of the separated protons and neutrons. And this difference in the energies, in the total energy of the bound system and the individual energies of all the individual particles, is called the binding energy. And you can think of the binding energy as how much do you need to add to break apart that nucleus into its individual parts. So if we look at this graph where we're plotting the binding energy per nucleon against the mass number meaning protons plus neutrons, then you can see the biggest binding energy per particle happens around iron and nickel. And so these are the most stable atoms. They are the most difficult to break apart. They are the most difficult to break into pieces. And so except for our light nuclei, and the other thing to notice is, right, so like for hydrogen, there's only one particle. So there's binding energy is essentially very close to zero. Helium, lithium, beryllium, boron, and so on. Except for these light nuclei, the binding energy is fairly stable. It does decrease a bit as we go towards heavier things, but it's much more leveled out than for the light nuclei. And it roughly hovers between 7 and 9 MeVs per particle. Now, I said a minute ago that the nuclei are only stable if the atomic number is less than 83, right? If the atomic number is more than 83, there are no stable nuclei. There are no nuclei where the nuclear force holding them together is strong enough to completely overcome the Coulomb force. And so your nuclei will start to break apart. And when I say that, I don't mean that they're going to just explode. I mean that they will just, lose a couple particles here and there around the edges, right, to make them more stable. And when they lose these particles, they emit energy. And so radioactivity is this spontaneous emission of radiation. Radioactivity happens typically for larger or unstable nuclei, right? So radioactivity, right, that is this emission of radiation, but it is particularly spontaneous radiation and it has to do with the decay of unstable nuclei. Right, which are typically heavy nuclei. And there's 3 types of radiation that can be emitted. You can have alpha particles, right? That's this symbol. And this alpha particle is the nucleus of a helium, right? It's essentially a particle that contains 2 protons and 2 neutrons. You can have beta particles. And a beta particle is either electron or a positron. So it's either an electron or a positron. And a positron is the antiparticle of an electron. It is identical to an electron in every way, except it's positive rather than negative. Or you can have gamma rays. And gamma rays are, right, a type of light or electromagnetic radiation. So alpha particle and beta particles, actual particles. Gamma rays are high energy photons, actual electromagnetic radiation. And so then the question becomes, okay, well, how do you tell these apart? And the way that we tell them apart is essentially with a mass spectrometer. We use a magnetic field, right? So what you do is you have your radioactive source inside here, inside of a lead container, because lead will block all of these kinds of radiations depending on the thickness. We just have a hole so the only thing is coming out is in one direction. And here I have a magnetic field. Now we know that the magnetic field exerts forces on moving charged particles, right? And our magnetic force is going to be Q, V, B, strictly speaking, sine theta. But here my theta will be 90 degrees and my sine of theta is 1 because these are going to come out in this direction, which is perpendicular to my magnetic field. And then using my right-hand rule, alpha particles, which are always positive, right? It's 2 protons and 2 neutrons, will get deflected up. Gamma particles, or gamma rays, are not particles at all, or at least they don't have a charge, they don't have mass, they're photons, won't get deflected at all. And then your beta particles, if it's an electron, will get deflected, in this case, down. And if it's a positron, it'd get deflected up, but because it has less mass than the alpha particle, it'll be deflected more, and it'll land up here. So then we can tell what kind of particle it is. Now, the other thing about these radioactive decays, right, these particles that are being emitted, is what they can go through, right? Because lead blocks all of them up to a point, right, depending on the thickness. But alpha particles are heavy and slow moving, and 4 atomic particles don't actually have that much energy, relatively speaking. So alpha particles can be stopped by a piece of paper. If it's a very thin piece of paper, they can get through, but just regular printer paper can block, for the most part, alpha particles. Beta particles can penetrate a few millimeters of aluminum. So aluminum foil will not stop a beta particle, but an aluminum pan would. And then gamma rays can go through several centimeters of lead. So you're going to need, 10, 20 centimeters, a foot of lead thickness to block most gamma rays. So essentially what happens is when you have these heavy, unstable nuclei, they will decay and they'll lose particles. And what kind of particle they lose depends on a number of factors, and we'll get into that later, but they'll lose one or more of these particles for each decay. And the total number of particles that they lose, that decay in a given time, is proportional to the total number of particles in your radioactive sample. So say you have a sample of uranium. Uranium is highly radioactive. It's going to depend how many of these particles that you will have emitted by your source depends on how many particles are you starting with, how many uranium nuclei or whatever other element we have are we starting with? And so the number of particles that are decayed, right? So this is how many particles decayed, or how many are lost, is going to equal negative lambda n delta t, where lambda is called the decay constant, n is the number of particles you started with. It's usually a very large number. And then t here is our time interval. And the decay rate, right, of a sample, meaning how many decays per second, the decay rate is delta n over delta t. How many particles are emitted per second, and that's just lambda n. And it turns out if we got, for a given element or for a given type of nucleus, if we plot what's called a decay curve, which is how many particles we have in our sample as a function of time. So this is not how many particles are we losing, but how many actual physical particles of that type do we have in our sample as a function of time. If we plot that decay curve, what we'll see is that it is exponential. So the number of particles at some time is going to equal the number that we started with, that's this n naught, e to the minus lambda t, where again lambda is our decay constant. So you'll see that this is an exponential decay. Now, often it is useful, people will talk about the half-life. And so the half-life is the time it takes to lose half your particles, right? So half your nuclei. Or the time it takes for half of the nuclei that you started with to decay into something else. And this half-life is going to equal the natural log of 2 over lambda, or 0.693 over lambda. Now the units of our radioactivity, the units of this radioactivity rate, is called the curie. And 1 curie is 3.7 times 10 to the 10th decays per second. So 1 curie is 3.7 times 10 to the 10th decays per second. And 1 becquerel, these are both named after scientists who did pioneering work in radioactivity, is 1 decay per second. Right? So the SI unit of radioactivity is the becquerel, right, which is 1 decay per second. And then the unit that's most commonly used is the curie, named after Marie Curie, which is 3.7 times 10 to the 10th decays per second, which admittedly is a lot. So next time we'll talk about specific radioactive decay processes and equations, and we will do an example.